here. Okay, so, all right, we have here a problem dealing in section 12.6 with surface area. Okay, surface area. Find the surface area for the part of the paraboloid that lies inside the cylinder. And we have a formula to find surface area, but what would be a good start to doing this problem, you think? What do you think would be a good way to start this problem? Draw a picture. That's right. Draw a picture. Okay. And we're going to do that. So let me go to the next page on this. All right. And again, we're trying to find the surface area of a part of a paraboloid that lies inside a cylinder. Okay. So let's go to the next page. Here's a picture. Here's a nice picture. So this parabola opens outward along the x-axis. X equals y squared plus z squared opens out along the positive x-axis. And it would keep opening, but it gets restricted by a cylinder. The cylinder y squared plus z squared equals 9. That cylinder is a cylinder. It's not an up and down cylinder. It's a sideways cylinder that also goes, whose center is the x-axis. Okay, whose center is the x-axis. So why do I need to draw the picture? Well, always we need to determine our limits of integration, right? We always need to determine limits of integration. And so, you know, that we have to do. That we have to do. The integration is not so much an issue usually for these double integrals, but finding the limits is for students. If the limits aren't right, you're not going to get the problem right. So, okay, so, there are two axes. Let's see, Christopher says, hold on, is my picture, I think my picture's okay. I'm seeing, oh, thank you, the Z is mislabeled. Thank you, Christopher. Let me fix that right now. Yep. This is a Z axis, absolutely. And let me correct that on my page as well. Okay, that's a Z axis. Okay. So, okay, now there are two ways to find the surface area. Okay. The first way is to parameterize a vector function of two parameters. Find the parameterization of the paraboloid, okay, because it's the paraboloid here that we're trying to get the surface area for. Okay, so we have to parameterize. We have to find the vector parameterization for the paraboloid if we're going to use method 1. But method 1 always works because, you see, you can find the vector parameterization for any surface. It doesn't have to be a surface. It can be any type of surface, okay? So it's a very general method. So I want to show you that method. So, okay, how are we gonna find the vector parameterization for this paraboloid? Well, the paraboloid x is equal to y squared plus z squared. So it makes sense for the x component for the paraboloid to let x equals y plus z squared. But then you'll just let y and z be free. So this parameterization is R is a function of parameters y and z. Okay, R in this case is a vector function of parameters y and z. Now, the parameters y and z have a restriction on them. The restriction is y squared plus z squared has to be less than or equal to 9. Okay, it has to be less than or equal to 9. Why is that? Well, let's look at our picture here. Let's look at our picture. The parabola stops when it meets the cylinder. And so the domain is going to be a circle, right? Because if we project the paraboloid into the YZ plane, you're gonna have a circle. You're gonna have a circle. So but think of it like this: for all points on that paraboloid, all the y and z coordinates have to obey this restriction. Y squared plus z squared is less than or equal to 9. Now, hold on, there was a chat here. Yeah, I know. Now, wait a minute. Hold on. Picture, yeah, yeah. This is a, hold on now, hold on. Wait. Okay, all right, we're good. Okay, very good. So here then is here's my region D. Here it is. All the points on the paraboloid, the parameters y and z have to obey this restriction that y squared plus z squared is less than or equal to 9. Well, then that's just going to be this circle with all the points inside. Okay, well, now we're going to use the formula here. We have to get the parameter, the derivative of our vector function. So with respect to y, the derivative is going to be the vector 2y, 1, and 0, those components. And the derivative of r with respect to z is going to have components 2z, 0, and 1. Okay, so are there any questions so far? All right. All right, may I move to the next page? Okay, Ryan's good. John's good. Okay, well, so next step is to take the cross product of these two derivative vectors. So we'll do that. I'm going to take the cross product, and I'm going to utilize the rule that we learned for a cross product, where we have a determinant of a 3 by 3 and do cofactor expansion along the first row. That's review. That's back in chapter 9 that you learned that. And what happens is the cross product of the derivative vectors is going to equal I minus 2yj minus 2zk. Let me give you a moment to catch up here, okay? Let me know if you have any questions. Okay, so, all right, now that we have the cross product of the two derivative vectors, we can now find the length of that cross product vector. We just take the square root of, we square each of the components, add them, take the square root of that, and now we have, well, we know what the integrand is for our surface area formula. We know what the integrand is. You notice that what I've done is I've kept the dA here, and I've wrote my region of integration just as y squared plus z squared is less than or equal to 9. I don't want to do too much at once for these on these kind of problems. You know, they can. You know, I don't want to be nervous. You know, I want to take things one at a time. So now I have my integral. Now I have to think about the limits. So, okay, we've learned that we can use Cartesian coordinates or that we can use polar coordinates to do integration. And based on my region D here, the y squared plus z squared is less than or equal to 9, would polar coordinates, which is a circle, right, closed circle, would polar coordinates be better, or would Cartesian coordinates be better? I agree, Ryan. Polar coordinates would be better. So now I'm going to fill in what the dA is, and I'm going to fill in limits for my double integral. Are there any questions so far? Let's see. Christopher says, can you use a modified polar? Sure, absolutely, absolutely. I'll show you on the next page here. Okay. Well, what I had here. Well, actually, hold on. Let me go back to the previous page. So, what I'm going to do is I'm going to let y. I mean, based on my circle here, I'm going to let y equal r cosine of theta, and I'm going to let z equal r sine of theta, and then of course y squared plus z squared would equal r squared. Right? That's certainly true. So where I have the, you know, like in this, okay, in here, this here is just 4 times y squared plus z squared. And so using polar coordinates, I'll replace that. Hold on. I'll replace that y squared plus z squared with r squared. And so I'm going to get then, in the integral, I'm going to have the square root of 1 plus 4r squared. And of course, my dA for polar coordinates is, as you know, r dr d theta. And then based on the region D, that circle, that's a circle that goes from radius, well, the points in the circle go from radius 0 to radius 3, and the angles for the points that compose that circle go from angle theta equals 0 to theta equals 2 pi. Are there any questions up to here? Okay, so now class, we have I iterate the integral, and I'm going to let u equal 1 plus 4r squared. Then du is 8r dr, and so 1/8 du is r dr. And then the inner integral becomes this integral here. The integral from 1 to 37 of the square root of u times 1/8 du. Let me let you just copy down to here. I think then these other steps you'll be okay with, but let me know if you have any questions. Okay, so are there any questions so far? What I did was I pulled this constant out. I pulled this constant out of the integral. And so now all I have to do is this integral right here. And that's a pretty easy integral. So let's go ahead then, if we're good, let me go to the next page to finish this out. Okay, so the area of the surface, it turns out, is going to be, and this is the exact answer, and that's the answer, as you know, WebAssign would want. Okay, so for a Thursday, you have a section 12.5 and 12.6, some problems due. They're both small assignments. Okay, but you know, this should be helpful, right? Absolutely beautiful answer, of course. Okay. All right. So this is fine. Now there's another method also that you can use. Okay. This works because x can be written. This second method works because x can be written as a function of y and z. If you had like a cylinder, let's say you had something different. Let's say you were trying to find the surface area for a cylinder. You couldn't use method 2 because a cylinder cannot be the equation for a cylindrical surface cannot be expressed as a function of two variables. You can't write like for example, just as if you had like x squared plus y squared equals 16, right? That's a vertical cylinder, that it goes up and down. But you can't take z and write it as a function of x and y for a cylinder, right? That you can't do that. So that means this second method can't be used. Okay, but so that like in the book, they talk about how if z is a function of x and y, you can the original formula in part 1 for the area of a surface that can be rewritten as another formula, another equivalent formula. But that won't work unless z can be written as a function of x and y. Well, in our situation, of course, we're talking about, okay, x is a function of y and z for the paraboloid. And because of that, we can use this formula here for the surface area. Okay. And that's surface area of a graph formula. Okay, and what happens is if you differentiate x with respect to y and differentiate x with respect to z, you're going to wind up with what we had in when we did method 1. You're going to wind up with the same double integral, and so the surface area would naturally be the same. Okay. So I wanted to show you 2 different ways to do this kind of problem. I wanted to show you 2 different ways to do this kind of problem. But again, remember that this second method will not work all the time. Maybe on exam 4, you'll have a surface where you can't use the second method and you have to use the first method with the general formula, just to let you know. Okay, so let me give you a moment to think about that. All right, are there any questions before I stop the recording here? How many, did you find this to be, was this a helpful example, class? Okay, good, Ryan, good. Glad to hear it. Good, okay.